Hello everyone, we are Group 12. Today I'm going to introduce our final project for our class. Our topic is the exponential decay of social media attention, and you can see our members in the bottom right corner. First, I will introduce some key terms and our motivations. Then we will present the basic form of our model. After that, we will discuss and improve versions of the model with additional variables. And finally, I will introduce the most complete versions. And that is our motivations. As an engineer student group are in the age of social media, we want to know how attention to online content, like videos, change over time. For example, one of our teammates upload a video, then gain most of the attention within the first 100 days. And after that, the view count becomes saturated. This pattern resembles a decay function, which led us to think about modeling it mathematically. Even our professors are now showing the content online, so we believe that understanding these attention patterns could be useful not only for content creator but also for educator.
Glossary. Here are some key terms that will help you understand our model. Attention. The level of interest or engagement with the video. View. The number of times the video has been watched, also called cumulative attention. Go viral. When the video suddenly becomes very popular and spreads rapidly. Profit, the earning from the video, which usually depends on the number of views. On the right side of the slide, you can see an example of the viewership trend for a real video. It shows that the attention is high at first, but gradually decreases. This is the main behavior we are going to model. Next, let's look at the basic assumption we made for building our model. Basic hypothesis. In order to build a simple and effective model, we made the following basic assumption. First, attention will naturally decrease over time. Second, the video will remain permanently available online. Third, we assume that the number of people is infinite and each person watches the video only once. Fourth, all variables are continuous, except for the subscribed. This assumption allows us to model the system mathematically in a straightforward way. Then, based on this assumption, we can derive the basic form of the attention decay. Now let's look at the basic form of our model. We describe the change in attention over time using the simple exponential decay model. The differential equation is dn of t over dt equal negative lambda times n of t. When we solve this equation, we get n of t equals n naught times e to the power of negative lambda t. Here, n of t is the cumulative attention at time t. N0 is the initial attention when the video is uploaded. T is the time. Lambda is the decay factor, which controls how fast the attention decreases. A large lambda means a faster decline. This simple model matches what we observe in real data. High attention in the beginning and a gradual decline over time. Finally, in the next part, my teammate will introduce how we can extend this model to account for videos that go viral.
By looking at the basic model of how a video's view grow over time. We denote the number of views at time t as v of t. It's calculated by integrating the attention rate n of t over time. In this model, we assume the attention rate follows as an exponential decay, like the first formula in this slide. These equations show that views increase quickly at first, but eventually plateaus as attention fades out over time. Moreover, since profit is proportional to the number of views, we write this formula. This implies that maximizing views over time directly increases your revenue, which is critical for content creators. Next, let's consider the strategy behind when to upload a new video. Suppose at time t equal to t1, you decide to release a second video. Before that point, attention is decaying from the first video as the first formula in this page. But right after you upload the second video at time t1, the total attention becomes the second formula in this slide. This means your audience attention is now the sum of the two decaying attention curves. The first terms still represent the old video, while the second terms represent the new one starting fresh from time t1. So by uploading a new video, you're reviving your attention curve, keeping your total attention higher. This model helps us visualize why it's important not to wait too long between uploads, or you risk losing all momentum. Finally, let's explore what happens when you upload video on a regular schedule, say every t unit of time. In this case, the total attention at time t becomes the sum of all previous decay attention waves, like the formula. After simplifying this geometric series, we get the second formula in this slide. This tells us that if you consistently upload content every t time unit, you can maintain a stable and possibly great level of attention over time. Now, let's say you don't want your attention level to ever drop below a certain fraction p of its maxima. Then you can compute the required upload period t from the last equation in this slide. Let's take an example. If you want your views to stay above 80% of the peak, just plug p equal to 0.8 into the equation, and that tells us how often you need to upload. This model provides a quantitative method to optimize upload frequency and maintain high engagement levels.
Finally, let's look at the general solution to this viral growth model. We solve this by substitution. We arrive at general form. This formula describes how a video's popularity grows or fades over time, depending on the values of lambda, alpha, and p. The model can represent normal decline or explosive viral behavior, all in one elegant expression.
We add even more depth by introducing complex numbers. We assume that attention G is made of two parts, N for social attention and M for the probability of going viral. So we write it as G equals to N plus IM, which I is the imagined unit. This let us capture both real-world attention and hidden viral potential. We can treat attention as a wave-like process over time and space, similar to how heat and sound travels. The equation we use is a partial differential equation. In this equation, D tells us how attention spreads between people. Omega reflects periodic viral behavior and lambda still represents natural decay. Although solving these is complicated, the model gives us a way to predict when and how attention might spike, due to hidden factors like influencer interactions or algorithm boost. To warm up, we started with simple exponential decay, then added terms for periodic uploads, viral growth, and finally modeled attention as a dynamic wave-like process. Through this project, we hope to better understand how online attention works and how creators might use mass to reach and sustain their audience. Thank you.